there is a natural basis function, right? 1x square. How to do orthogonal with a 0, 1? Like dimension orthogonalization. 2 marks are given for that. If you practice, you get 2 marks minimum. Other questions I cannot tell, but non-linear ODE, one question I think coming. ODE from assignment I picked up one problem. If you practice the assignment, you can get the problem. 8 marks. So 8 plus 2, 10 marks are given to you. Any other questions? 8 marks question is coming from the assignment. Problem set 6, right? And one question is coming from there. From which page? Back page. I am giving the number also. If you ask me more, I will tell you the number, which number I have given. Front page I have not given. Back page, second page, there are 2 pages, right? Second page I have given the problem. So if you can pick up from that, you will be lucky to get 8 marks. 8 or 7 marks, I don't remember. And that 1x x square 2 marks is based on 1x x square. Some other problem is given that you can see tomorrow. So that is the thing. How was your thermodynamics test compared to mathematics? Was it better? Better or worse? What is our opinion? Huh? Better, huh? Worse, huh? How many guys think better than the thermodynamics was better? No idea. Thermodynamics. Okay, how much is the highest mark for thermodynamics? Huh? We have not got it. We will be getting next class. That I know. Any guess how much is the highest mark in thermodynamics? Huh? No. How much is the highest mark in mathematics? 70. Just 50% of it. 8.5, right? Yeah. So that was the thing. I thought I am a very bad guy. I really gave you very bad marks. But I was looking at thermodynamics marks. I was shocked how much lenient actually I was. Maybe I may be a bit tougher in the second quiz, but the question is already over. I already gave you 10 marks in the second quiz. Any other questions? No questions. Okay, attention please. Okay. We'll be talking about, we are discussing about the adjoint theorem and doing some numerical problem, right? We have given a problem which is talking about the operator is self-adjoint or not. Self-adjoint means L equals to L star, B equals to B star, and the problem was dpu by dx square. You see that write the problem, and yes. So that is the part we actually saw. So LU is dpu by dx square, and the domain is 0 to 1. Domain is 0 to 1. This is the domain. And subjective conditions u0, which is 2u prime 1, and u1 equals to 0. So investigate whether the operator is self-adjoint. That means adjoint theorem. Okay, of course we formulate adjoint theorem. Bilinear concomitant has to be 0 because you have to prove L equals to L star. You have to prove inner product LUV equals to UL's inner product UL star V. The bilinear concomitant part should not be there, right? And to prove to incorporate bilinear concomitant, we will get the B star. So from here we get the adjoint problem. From here we get adjoint problem, and from here we will get L star and B star, right? From here we get L star and B star. So if you do LU inner product LUV, what you get? You got something, right? We got the JUV. What was JUV? First you write LV JUV and then the UL star. What is JUV? U dx into V 0 to 1 minus U dV dx 0 to 1 integral 0 to 1 U d to V dx square dx. Of course n equals to L star. But we don't know what's about V, whether V equals to V star or not. For that purpose, we need to write separately JUV, which is du dx V at 1 minus du dx V at 0 minus u dv dx at 1 plus u dv dx at 0. Now you see that for the boundary condition, u1 equals to 0. You can happily put 0 here. But it's not the case for u0. u0 minus 2u prime 1 equals to 0. So if you want to write, you can write this way: u prime v1 minus u prime v0 plus u v prime at 0. And to make it self-adjoint, we have to first prove inner product u v equals to L star v, and this entire thing has to be 0. Otherwise, we cannot have adjoint theorem, which is an inner product u v equals to L star v, which is a necessary condition to establish Z equals to L star and V equals to V star. And from that JUV, you can get the necessary boundary condition for the L star operator. Okay. So, what will be the condition for the V such that this entire thing, we can actually write a very simple thing from here. If you put V0 equals to 0, this term will go. Okay? And then what actually happens? Which is u prime 1, V1, and then plus u1 v prime 1 equals to 0. Sorry, u0, then u0 is what? 2u prime 1, then what is the condition then? v1 plus, how to get it? If you want me to do one more step, u prime 1 v1 plus 2u prime 1 v prime 0 equals to 0. Is that correct? So we got the v1 plus 2v prime 0. So that's the so if you see that u prime 1 is common here. Okay, so it is so if we take in the bracket v1 plus v2v prime 0, it's coming, which is becoming 0. So your v star operator is having v star boundary condition, which is how to write, which is v star v equals to 0, and which is nothing but, you write this way, v0, and which is v1 plus 2v prime 0, which is v0 equals to how much? 0. And this is 0. But this boundary operator is not the same boundary operator here. So the operator is not self-adjoint. So the operator is not self-adjoint. Is the fun clear? The operator is not self-adjoint. Now we have done enough for the self-adjoint operators. We have done adjoint. This much of what we didn't have in vector space. Why? Because we didn't have the concept of the boundary condition in vector space, and we didn't have the concept of the bilinear concomitant. So we didn't have the concept of the bilinear concomitant, and we didn't have the concept of the boundary condition. Okay, so that's what this extra work has to be done for the functional space. Now, I think we have done enough, and I think next part is coming is of course we have seen the basis function, we have seen the orthogonal basis function, we have seen the orthonormal basis function. Now, it is the right time to talk about eigenvalues and eigenvectors, not eigenvectors, eigenfunctions. So we are talking about eigenvalues and eigenfunctions. When we are talking about eigenvalues and eigenfunctions. So for the eigenvalues and eigenfunctions, we will be talking in terms of the self-adjoint operator, because we know that any operator can be converted to a self-adjoint operator. If you don't understand that part, please refer to your class note. We have proved for a0 d2u by dx square plus a1x du dx plus a2x u equals to minus a3x something was there, and from there we convert it to the self-adjoint operator, which is d dx px du dx plus qx u equals to minus lambda wx. This is the case for the self-adjoint operator. So, like vector space, we won't talk about non-self-adjoint operator here. That's the basic. That is the one of the advantages. One advantage here is we won't talk about non-self-adjoint operator, because we know that from the start of the theory, any operator can be converted to a self-adjoint operator. There's a transformation, which is px. We have seen integral of a0 by a2x. So many transformations we have done. Qx. So one correspondence is that so any operator given to you, you can convert to the self-adjoint operator. So essentially, any operator can be expressed in terms of a self-adjoint operator. Okay. So there are two things here. In the vector space, we have seen the eigenvalues of the self-adjoint operators are real. We have proved it, right? So for here also we have to prove that eigenvalues of the self-adjoint operator. Of course, I am assuming that b equals to b star. This is the assumption. Otherwise, you cannot say the operator is self-adjoint. Okay, L equals to L star doesn't mean the operator is self-adjoint. B has to be. So base thing is that what are the boundary condition? U0 equals to 0, U1 equals to 0. Okay? U0 equals to 0, U1 equals to 0. So for any eigenvalue problem, if you want to fix up the boundary condition, and we actually show that the boundary condition has to be homogeneous boundary condition. The boundary condition has to be homogeneous boundary condition. Okay? Because we know that for any eigenvalue problem, any such problem, you have the operator which is L equals to L star, and B equals has to be B star, and B is the boundary operator. The boundary operator means the boundary condition has to be such that. So, and we have seen that U0 and U1, this kind of boundary condition will be same for the adjoint problem. If the operator is self-adjoint, we have already done it. There are two problems I have done previously. First problem, the second problem I discussed today. First problem, if you look at that, we have this kind of boundary condition, and we have got the same boundary condition, same boundary operator for the adjoint problem. So it is better to have the homogeneous boundary condition to make sure your operator is self-adjoint, and complete self-adjoint means A equals to L star and B equals to B star. For that condition, the first rule was the eigenvalues cannot be complex, have to be real. That we have proved already for the vector space. Eigenvalues have to be real. Okay? So what is our equation? LU equals to minus lambda wx. This is the typical eigenvalue problem. You remember that vector space eigenvalue problem was Ax equals to lambda x. Here the eigenvalue problem is AU equals to minus lambda wx. Vector space it was AU equals to lambda. That is the vector space problem. A equals to lambda u. Here it is AU equals to minus lambda wx. This is very, very important. Actually, I will show you in some demos, some problem that why it is minus. If it is plus, it cannot be eigenvalue problem. Okay? Why it cannot be eigenvalue problem? See, eigenvalue will give eigenfunction, like eigenvalue will give eigenvector. We have seen that eigenvectors have to be non-trivial, right? If eigenvector is trivial, there is not eigenvector, right? That's the determinant of A minus lambda y have to be 0, because A minus lambda u equals to 0, and u belongs to the which space? Non-space. U belongs to non-space, and since u belongs to non-space, determinant of A minus lambda have to be 0. Otherwise, you won't get non-trivial solution. Similarly, here we will show that if this is plus, then there is a chance to have the eigenfunction b 0, and in that case, plus with the plus we cannot have the eigenfunction problem, and that's why we will get this kind of situation. We will take a toy problem to demonstrate that part. So our L is, what should the L for this case? What is that L? ddx of p of x ddx plus qx. This is my L. So how to prove this? We have done for the vector space. If you remember, you can tell me how to prove. Inner product of what we have to prove? We know that LU V UL star V, and for this operator it is known that bilinear concomitant will be 0. We have proved it. Bilinear concomitant will be 0. And in that case we can also see that V star also will be having the same kind of boundary condition. Okay, so for this case, how to start the proof? The eigenvalues have to be here. How to prove that? LU with U, exactly, you are right. LU equals to minus lambda Wx. Am I correct? Yes. So from here we can write LU equals to U L star U. Left hand side part is done. Right hand side. U L star U. And then what can you write? L star is L. For our case, L equals to L star. It has been proved already. If you want how to prove it, you go back to the two previous classes back. There we have proved it. This is a self-adjoint operator. Okay? L equals to L star. So since L equals to L star, what you can write? We can write U minus lambda Wx U. What actually happens in that case? What to write? Or inner product property? We have done inner product property. Minus lambda bar. Wx is the function scalar, so it is the same. Okay. So what actually happens? So left hand side equals to right hand side, and what we get? We get lambda. In fact, what we should do here, we can write U Wx U. Keep in touch, keep intact. This one is better. I will show you why it is like this. So lambda U Wx U equals to minus lambda bar U Wx U. Slight mistake is there, please correct it. So far everything is okay, right? Yes? Okay. What you got? I will get one more step here. Integral 0 to 1. I am just using the definition of inner product. What's the definition here? Wx, Ux, Ux, dx. Very fundamental way. Lambda bar 0 to 1. Ux, Wx, Ux, dx equals to 0. Right? This is the way we define the inner product, and you see that what you are seeing here, you can see this is like a weighted inner product. This is like so first time we are seeing something called weighted inner product. Generally, inner product is a integral UV. If by domain is 0 to 1, we write 0 to 1 Ux dx dx. This is the way we write. But here we can see that there is something called double function. Sometimes what we do, we put a weight here 0 to 1 Wx. So this is called as weighted inner product, and weighting is here. So sometimes when you do gravity speed orthonormalization, sometimes we use weighting function Wx. Okay? And based on the weighting function, we get the kind of polynomial we have heard, something called Hermite polynomial, Legendre polynomial. Okay? So Hermite polynomial one, the weighting function is 1 by square root of 1 minus x square. So if you have on x square basis, and if you have the weighting functions in square root of 1 by square root of 1 minus x square, you get a series of orthonormal polynomials, which are basically Hermite polynomials. So Hermite polynomials are orthogonal with respect to the weighting function. So this kind of weighting function concept was not there in the vector space, right? The functional space we have seen, now we are seeing that it is called as u w minus lambda bar, again the same form, u w equals to 0. And what we have? Lambda minus lambda bar, inner product, u equals to 0, and this is the length of the vector or length of the function. Okay, so lambda minus lambda bar equals to 0, and lambda equals to lambda bar, and we can say that eigenvalues are clear. Are not clear? Yes. 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 Any questions, doubts? Yeah. Pardon? Yeah. The weighting function is the weighting function, right? Definition. So what do we do in the? This is 1x square. You remember the Gram-Schmidt normalization? The Gram-Schmidt normalization, what we do? We use inner product, right? Okay. What is the definition of inner product there? The normal definition. But here, if I say Hermite polynomial, I will say that weighting function equals to 1 by square root of 1 minus x square. That means whenever you use the inner product definition, we have to use inner product UVW, where Wx is squared by 1 by square root of 1 minus x square. In that case, we will get phi 1, phi 2, phi 3. And those phi 1, phi 2, phi 3 are called as Hermite polynomials. Similarly, we can have the weighting factor square root of 1 minus x square. So like that, you have the Legendre polynomials, Hermite polynomials, and so on. So all those polynomials are hard, but the basic is the same, that 1x square. So we don't have to remember anything. If you remember 1x square, all the set of polynomials we can derive from there. Right? Yeah. Okay, this is okay. Is this okay? This proof. Second thing is that we have in a vector space. What was the restriction? Eigenvalues are real. Anything else was there? Eigenvalues could be negative or positive, both, right? It cannot be complex. Here also it cannot be complex. But functional space, we are going to prove that eigenvalues are non-negative. Eigenvalues are, that means eigenvalues cannot be negative. It can be 0 or positive, but it cannot be negative. It cannot be negative for the functional space problem. So let's look at the eigenvalues for this same operator. And the postulate what we are going to say here. The eigenvalues of the self-adjoint operator are non-negative. Okay. So what we have? We have LU equals to minus lambda Wx. These are our typical eigenvalue problem. U is the eigenfunction. And what we have in our product is U minus lambda Wx. Next step, integral 0 to 1, LU is ddx, px, du dx plus qxu dx. Am I correct? Left hand side equals to minus 0 to 1 lambda wx ux dx, sorry, u square x dx, lambda wx. It should be slight mistake, I did miscalculate because LU equals minus lambda wx, not lambda wx. So it should be lambda Wx u square x dx. Correct? Yes. Okay. Next, you know how to do it. All bilinear complement, everything will be coming. Give me the answer. I won't expand it. You have done enough of this business. You give me the answer. So what you got here, you will give me the answer. First boundary condition from here is there. If you don't know that answer, you please go back to your class note. You don't even know how to copy from the class note. Your class note, all answer is there. Look at the class note, get me the answer. What's the first boundary term from here? U of x p of x du dx, right? 0 to 1 minus integral 0 to 1 px du dx whole square dx plus 0 to 1 qx u square dx equals to minus lambda 0 to 1 wx u square x dx. Am I correct? Yes. Imposing the boundary condition. You have the boundary condition. What boundary condition you have? u1 equal to 0 is equal to 0. Right? If you do that, this term is going to 0. Right? And then what you get? From here, what you get? Lambda. Two terms are there. So this minus will go, so it is nothing but 0 to 1 px du by dx whole square minus qx u square dx 0 to 1 w u square dx. Now I will show you here why lambda will be non-negative. Now for chemical engineering problem or any fluid mechanics heat transfer problem, mass transfer problem for chemical engineering, we consider three coordinate systems: Cartesian coordinate system, cylindrical coordinate system, spherical coordinate system. And if you look at them, it can not express like this. For example, you might have seen ddr of 1 by r du dr. This is like cylindrical coordinate system. Okay? Spherical coordinate system, what will be that? Do you remember? R square, right? Yeah, 1 by r square term will be coming. Okay? Please look into it in the Bastard live flow. So, based on that, based on coordinate system for our case, generally P is greater than equal to 0, Q is less than equal to 0, and W is greater than 0. This is a basic coordinate system. You go back home, look at Bastard live flow index or any kind of Cartesian coordinate, cylindrical coordinate system, spherical coordinate system, you see this kind of things will happen. And if you look at this is positive, okay, and if since Qx is negative, this entire will become positive. So this is positive, and lambda cannot be negative. Okay, maybe what may happen if these two are equal, in that case lambda can be 0, the worst case, but lambda cannot be negative because of our case based on coordinate system. We go back home and try to look into that. Okay, so this is one of the extra properties compared to the vector space. Next we will be talking about the eigenfunctions. Eigenvectors are found to be orthogonal in self-adjoint operator vector space, right? Please look at the proof what we actually have derived in the previous class. Eigenvectors are orthogonal for the self-adjoint operator in the vector space. In a similar manner, it is possible to prove that eigenfunctions are orthogonal in the functional space. How to prove it? How to prove it? How to prove it? We have done the proof. How to prove it? to prove it in vector space? LUV equals to UL star V. For us two eigenfunctions, I am saying UNX and UMX are two eigenfunctions. By the way, can you guess how the eigenfunctions will look like? We have not seen. We are only talking about the eigenfunction. How the eigenfunctions will look like? Is it like 1x square? What the eigenfunctions will look like? Any idea? You pick up one simple operator, d2 by dx square. If I want to find out the eigenfunction of the operator, like a simple matrix you can take 1 0 0 1. You can easily find what the eigenvector. What are the eigenvectors? 1 0 0 1. Quickly you can tell. 1 0 and 0 1. And what is the beauty? Each column are the eigenvectors. Each column are the eigenvectors, right? Okay. So then what actually happens? d2 by dx square. Can you quickly tell me what is the eigenvector? You know how to find eigenfunction. d2 by dx square, how to find eigenfunction. It is by nature self-adjoint operator, right? Then how is the eigenfunction formulation? How to find the formulation? d2 by dx square, I want to find the eigenfunction. How to find eigenfunction? Because we are talking so much of eigenfunction, you don't even know how they look like. You should know how they look like. That's why I'm asking the simple differential operator d2 by dx square. Simple differential operator, how they look like. Any idea? d2 by dx square. What's the eigenfunction formulation? If you use the eigenfunction, how to write the eigenfunction eigenvalue problem? We write ax equals to lambda x. X is the eigenvector. Similarly, d2 by dx square equals to lambda. Ws is how much for this problem? Check your notes, man. You are not looking at the notes. You don't remember. You don't look at the notes. You are becoming so lazy. What is Ws for d2 by dx square eigenvalue problem? What is Ws? 1. So it is what kind of what is the thing? What did you get? Eigenvalue problem. How to formulate? d2u by dx square, use the eigenfunction. How to write? Right hand side. Minus lambda. Just now you said omega equals to 1 and somebody is saying omega. I don't know. What is there? The brain, my brain or your brain? Ws is 1. It can be done from the class 460% Ws. How to solve this problem? This problem you have done in your school level. In 10 plus 2, this differential equation you have solved. What is the difference? What is the solution? And now we know that lambda is always positive. Or 0. Lambda cannot be negative. What is that then? It takes so much of time. You have done school level, you have done so much of differential equation, you have taught so much of differential equation, it takes so much of time. E raised to. We have done it, man. Tomorrow is your exam and this is the syllabus. This problem is in the syllabus. Tomorrow is your exam and entire class is silent. Nobody can give me the answer of the solution. d2u by dx square equal to minus lambda u. What is the solution? This has been done in the school level. People are looking at, yes. What sign? What plus or minus? Boss, you have brain or what? I think you have a brain. At least one. Come on. d2u by dx square equal to minus lambda u. This we have done so much in the differential equation. Tomorrow is the exam. You are not able to tell me the answer. I am shocked. I don't know which grades I am issuing for the math course. d2u by dx square equal to minus lambda, your lambda is positive. What is the answer? d2u by dx square, I am shocked. d2u by dx square minus lambda equals to minus lambda u, which is d2u by dx square plus lambda u equals to 0. What's the solution? Entire class is silent. I am very shocked. What maths I am teaching? What maths I am teaching? U equals to no constant will be there. A cos what? A cos plus B sine. What are you talking? Can I teach like this in the class? A cos lambda. In fact, in the school level, I remember it is d square plus lambda equals to 0, d equals to plus minus root lambda. All those things we have done. Even you can put now solution. Boss, what are you doing? It is minus root lambda, right? Plus minus root lambda. Or I root lambda, right? So what is that? I have proved in the class, if it is e to the power I theta, e to the power minus I theta, use the Moivas rule, those kind of things have been taught already. Boss, I don't know what kind of mathematics I am teaching. I should leave this class and go. What is that? Answer. A cos root lambda u plus b sine root lambda u. It takes so much of pain for me to get this answer. It takes so much of pain. I mean, do you understand how it coming? How it is coming? Do you understand this? How? You tell me how. How de Moivre's that I already told you. You don't think I am a fool. You are fooling me. I don't think you know that answer, right? How it comes? Can you prove it? How it comes? Vasudha. How to prove it? I have done the proof in the class also. How to prove these things? Your trial solution n square plus lambda equals to 0. A is plus minus root lambda. Right? So solution should be u equals to c1 e to the power minus root lambda into u plus c2 e to the power minus root lambda u. This is coming directly from the solution. How this is coming? That's what I am asking. You told just like that. I can also teach just like that and go out in the class. There will be after me how it is coming. Yes.
E to the power lambda u I becomes lambda I u.
It is basically I root lambda I minus I root lambda. Okay? Because of plus minus root lambda. So e to the power I theta equal to cos theta plus I sin theta. If you prove it, you can see the constant C1, C2 is coming. That's why I wrote A and B, not C1 and C2. This kind of things I have taught in the class. I don't know how many times I did the same thing. I don't know what the entire class is. I'm really shocked. Even these kind of things should be coming in the GATE exam. At least for the sake of GATE exam, you should read it. I'm sure that 50% of the guys will be leaving next semester. I'm teaching for free in the GATE exam. That you are not even taking my coaching for free. Okay, u and x are two eigenfunctions. So now you can see the eigenfunctions nothing but the cos and sine functions. So you have got an idea. But simple operator dt by dx square, eigenfunctions nothing but the cos and sine functions. So now these two eigenfunctions are orthogonal. How to prove it? How to prove these eigenfunctions are orthogonal? How to prove these eigenfunctions are orthogonal? What's the first step? Amit, what's the first step? Inner product? L? That's what I don't know. You are talking like Hebrew to me. Tomorrow is the exam. I don't know how you do that. Lu and x, comma, umx equals to not integral. What integral? What is the idea of the problem? Lu and x equals to minus lambda wx un. What is the problem? This is the way I have done it. I told to follow the same procedure in the vector space. We are not following the procedure. Do you have the notes with you? I don't think so. Yeah, then please dictate from the notes. It is then a vector space. Yes. What is that? What's the next step? Minus lambda should come out. And then wx, unx, umx. Right? Right hand side is unx, L star. Am I correct? From the adjunct theorem, inner product LUB equals to L star means with the LUN equals to UN L star UN. L equals to L star for the self-adjoint operator. Of course, all this form, everything is self-adjoint. And we can write UNX L of UNX. Okay, this is lambda L. So LUN is minus lambda L WX UN. LUM is minus lambda M WX UM. Right? Our eigenvector problem we have AUI lambda I UI. You remember that? Same way. So it is, and here we know that lambda is real. So what actually happens next step? What actually happens the next step? What will happen the next step? Boss, I don't know what I am teaching. Nobody is talking. Nobody is giving me the answer. Minus lambda M UNX comma WX UMX. Remember that WX cannot be taken out because if you do the integral WX, the function of X, it should be in the inner product. You cannot take it out. If you take out, that means the assuming is constant. This is not correct. So that's why WX should be there. And of course, all the time the inner product looks like this is the weighted inner product. So left hand side equals to right hand side. So what we can write lambda n UNX comma UMX. We can write W here, which is weighted inner product. That's simple. Which is equals to lambda n UNX UMX W here, okay? So what we can write? Lambda n minus lambda m inner product UNX UMX W equals to 0. Lambda n cannot be equals to lambda m and UNX UMX W equals to 0. That means eigenfunctions are orthogonal with respect to the weighted inner product space. So here we conclude that in a generalized manner the eigenfunctions are orthogonal with respect to the weighted inner product space. It is not orthogonal by heart. If Wx is not 1, you cannot simply write UNX equals to 0, which is not correct. Inner product UNX UMX with respect to Wx, that means weighted inner product space, is like a weighted inner product space. So orthogonality with respect to the weighted inner product space. Okay? That means if an operator is non-self-adjoint operator, of course for non-self-adjoint operator it is possible to find out the eigenfunctions, and in that case those eigenfunctions for non-self-adjoint operator will be orthogonal with respect to Wx. With respect to Wx. Panda is there? Yes or no? Yes? So let's take up our previous problem. Just now we have done it. So we have done all the properties. So the operator is d2 by dx square. This is the operator, and our eigenvalue problem is like this. This is the boundary condition. What's the eigenfunction? That's my question. Can you tell me quickly what's the eigenfunction? Ux. What is the eigenvalue first? And what is the eigenfunction? You tell me first eigenvalue. Because what we have seen earlier, we have to verify the eigenvalue has to be non-negative. Eigenvalue has to be non-negative. We have seen that A cos what is that? Quickly. What is that? What's the eigenfunction we found? U equals to A cos root lambda u plus B sin root lambda u. What are A and B? Oh, sorry. What is that? u0 equal to 0. That means what? u0 means a will be there. This part will be going to 0 because sine of 0 equal to 0. That means what? A will be 0. Then your eigenfunction is now b sine root lambda x. So then u1, which is b sine root lambda equals to 0, which is sine n pi. Am I correct? Yes, not 2n plus 1 pi by 2. Sine n pi. Okay. So root lambda equals to, so b cannot be 0. Of course, in that case, sine root lambda equal to root pi, so n pi. So lambda equals to n square pi square. N square pi square. So now, if n equals to 0, what actually happens? Still you can get the eigenfunction which is constant. So n can be equals to 0. Sometimes n may not be equals to 0. So if n equals to 0, what's the eigenfunction? Can it be 0? Yes. So that means n cannot be 0. N has to be 1. Because we have proved that eigenvalue, eigenfunction cannot be 0. So the eigenfunction is not 0. That means n equals to 1, 2. And how many will be there? Infinity. Why? Because functional space dimension is infinity. So you will get infinite number of eigenfunctions. So eigenvalues. So it is pi square, 2 square pi square, 3 square pi square, and so on. Am I correct? These are the eigenfunctions, eigenvalues. Am I correct? Yes or no? And what are the eigenfunctions? What is the eigenfunction? Sine root n pi. Sorry. N pi x so what is the eigenfunction? Basically it is b1 sine pi x, b2 sine 2 pi x, b3 sine 3 pi x, and bn sine n pi x, and then infinity. Because infinite, why? Because functional space is of having infinite dimension. How to find b? You do integration, and it can be proved. It has been proved that they are orthogonal. These eigenfunctions we have proved it. So if you take integration with respect to sine n pi s, what is bn? What is bn? This is an orthogonal function. What is bn then? How to calculate bn? Okay, so that you actually see. So basically, use the functional space. So this is actually function. This is the eigenfunction. How to calculate bn, that you can actually see from the functional space. So this is your eigenfunction. Okay, and if you express a solution in terms of eigenfunction, you can calculate bn with respect to that. Means if you have fx, which is the combination of all sorts of eigenfunction, you can actually take inner product with respect to sine n pi x, and bn will be inner product of fx sine n pi x by inner product of sine n pi x and n pi x, because this may not be orthonormal, is orthogonal function. So we'll be discussing more on this problem. Tomorrow I am taking 2 classes because we have missed so many classes. Tomorrow class will be at 4:45 till 1.5 hours. So tomorrow we have class. Tomorrow morning is the exam. Same sitting arrangement. Some half of the people will be 355.